Last time, we tried to use the diffusion thermal instability on the stability of a premise frame, and instead of the theory coming from the lambda instability based on hydrodynamics consideration. And Lewis number effect gives us some understanding on the possible unstable premise frame. And we figure out if Lewis number is smaller than 1, usually when you have a rich hydrocarbon premise frame, you may have different kinds of not parallel or not planar or flat frames. Sometimes you may have the so-called cellular frame structures as shown in these figures. And this experimental observation basically were presented by Maxton in 1949 to give the idea about the possibility of for some butane mixtures with different kinds of pressure operations. And you can see there is just like some kinds of so many bubble surface, curved surface put together and as a so-called, this is a cellular frame. Actually, this kinds of frame tell you originally they may have a flat or planar frame, but by the inference coming from the outer perturbations, then the frame will becomes unstable. They shift from the original planar frame to another so-called cellular frame. That means they cannot come back to the original state. Then we say this kind of frame is unstable. The other experiment observation, actually, we present the frames stabilized in a coaxial stagnation point flow. The coaxial stagnation flow actually composed of the inner jet with outer jet, and both of jets can be controlled. Has different kinds of mixing ratio for the propane. Okay, and in the experiment, when you change the concentration of the inner tube or you change that in the outer tubes, then you can see different kinds of frame structure uh, appearance in the stagnation point flow. And here they tell you the frame instability can be observed based on the strip frames. Sometimes you can have just like a pudding shape, or sometimes you will have a pipe shape frames, and those kinds of curved frames represent the unstable premise frame, especially for the Lewis number smaller than 1. In this case, the mixing of propane with the air corresponding to rich conditions, and you can examine that for the rich propane mixtures. They always have the Lewis number smaller than 1. Then you can have this kind of strip frames. The third example, I want to show you those kinds of frame instability occurs on the Bunsen frames. And in this experiment is very exciting because actually this experiment I did not. This is not my project, okay? But actually, I helped my colleagues to do the experiment, and this experiment is, I tried to describe a little bit because this is a very nice experiment, and we performed it almost 30 years ago. Because at that time I was just a PhD student. I tried to help my colleague to take pictures on the frame structure, and you can see there is the frame. There is an experiment system shown here. You can see there is a very simple pipe, okay, and we let the mixture of propane with the air and going through this long pipe. Then you will have a fully developed flow and impinging out from the exit plane of the burner. Okay, now you can ignite it. Then you can have a very nice, perfect cone frame, and all the products of the premise frame burning will be sucked out by this bucket. Okay, and there is a suction system through the bucket. Okay, and the left hand side tell you there is some flow meter we use to control the boiling flow rate for the fuel and the air. Okay, And here the difficult thing is we try to take a picture not just from the front side. Actually, we want to take a picture from the top. Okay, but you realize there is the hot product will go out upward to the suction system. You cannot take a picture, use your camera to face the top view, because the lens of your camera will be burned out when they face those kinds of hot products. Then we need to use the mirror to reflect the image from the top to the front sides. And I have my colleague to do this experiment, and turned out I take a very good, I took very nice pictures, and I keep those pictures as a very nice teaching materials. Let me explain a little bit about the observation from the experiment that we have. The first one, you can see when, in this case, we use the rich butane mixed with air. Okay, and then this is the basically this mixture represents the Lewis numbers more than one. When you have a Lewis numbers more than one from our previous discussions, they should give you the two important appearance. The first one, you can see when you have a top view to the your Bunsen friends, you can see there's a look like just a volcano, right? Okay, volcano, but there is a hole just at the center of the tip of your burner of your flame, and this open tip represents the influence coming from the Lewis numbers more than one, as we discussed earlier. For the Bunsen flame, you realize the tip of Bunsen flame will experience the compression, okay, negative flow stage. When Lewis numbers more than one, which means those kinds of influence based on the imbalance of the mass and the thermal and the heat diffusion will give you a certain negative effect on burning intensity. Then on the tip of Bunsen flame, the flame will become weaker. Then sometimes the extinction. The black hole represents there is the no flame appearance here. Okay, and this is the evidence you can see for the case of Lewis numbers more than one, influence coming from the Lewis number effect. Okay, the second one, you can see if you have a the view from the side view or from the front view, you can see there is so many curved surface. They connect together to form the cone frame, right? It's not a perfect cone. The smoothly has a smoothly surface, but now you can have some kinds of a curved surface, and they connect together to form as a cone frame. And you can see there is a when you calculate when you look at it, there is a three surface they connect together: 1, 2, 3, 4, 5, 6. Okay, and we call this a so-called polyhedral frame. Polyhedral means you have some surface and they connect together to form the total surface. Okay, and on those kinds of polyhedral frame I point out here, polyhedral frames. Okay, this is the third case we have. Cellular frame is the first case I try to introduce to mention the frame instability. And then the second one is a strip frame. Okay, this is a strip frame shown in the coaxial stagnation point flow. And this is the third one, a polyhedral frame. Actually, you can see from the Bunsen flame burner. Okay, now this is the original view in the experiment from the top view, side view, and the front view. You can see these two very important features for this rich butane air mixtures. And you can see this is related to the Lewis numbers more than one premixed frame. You can see there is a hole on the tip of your premixed frame, and there is the straight frame shape for this frame. And yeah, additional one I need to mention from the experimental observation, they can see there is an outer frame. Outer frame exists in the downstream of this premixed frame, right? And this basically is a diffusion frame because the mixtures of butane and air basically are rich, then you will have some excess fuel that in the downstream of your rich premixed friend, then you will have a diffusion friend out in the downstream. Okay. Now the main thing is, this is a typical example for the frame instability based on our discussion on diffusion, thermal diffusion and thermal instability instead of the hydrodynamic instability introduced by Randall. But there is something I need to explain a little bit, because in this experiment we do the extra experiment to see the change of the frame structure. In this experiment, okay, the front, the upper row tell you can have a different view to see the typical rich butane premixed frame, and they have a different kinds of features to emphasize the importance of the reasonable effect. Okay, but now we try to add a small amount of so-called inhibitor. Inhibitor means when you add these kinds of species of materials into your combustion zone or burning structures, then they will produce some kinds of the chemical reaction variations. Then you will find out they have some kinds of separations on the burning intensity or the continual procedures for the chemical reaction. Now, in this case, we add 0.36%. It's very small amount in terms of boiling ratio of CF3Br into our premixture, and you find out there is some very interesting thing occurs. The first one you can see, the curved surface disappear. Then the frame structures, the frame pictures to tell you the image becomes very nicely, nicely be smoothly, then smoothized. Then you can see this is the perfect cone frame, right? You do not see those kinds of strip shape frame. The curved surface disappear completely. You can see from the side view or from the front view, but the opening on the tip still exists. Okay, and here now we try to think about how come the addition of inhibitor can give you these kinds of possibility to suppress the instability of your premixed frame. Now this is the inference coming from inhibitor from our experimental observation. Then we try to explain it. Okay, now look at the CF3Br as an inhibitor, but when you add this inhibitor to the frame structures, because the inhibitor go through the high temperature zone, go to the reaction zone, this species will experience some in a high temperature environment, right? They will absorb certain heat. Those heats, when CF3Br absorb heat, they will start to have some dissociation. Okay, for example, here the major reaction we may found CF3Br when this species meet with the hydrogen radical, as you remember, I described in this bracket, and they tell you in our combustion process, we may have a so-called branch chain reaction, and I mentioned there is three intermediate species are very important. One is the OH radical, the other one is H radical, and the third one is O radical, right? Those molecules, because in the reaction, in each reactions, they can produce the one carrier, from the one carrier to produce the one carrier for OH. But for H, they can produce two carrier, especially for B and C. And for O, they can produce two active species, OH and H. And those kinds of chain carrier will promote all the multi-state chemical reactions very fast. Okay, which means the existence of these three kinds of intermediate species are very important, particularly OH, H, and O. And in this case, you can see when you have a dissociation, of the CF3Br by interact with the H, then you can produce a so-called HBr, this species, and plus CF3. Okay, now the next serious chemical reactions will become more important because now HBr, this is a relative easier to react with the H here. You can see they will meet again with H, and then they will have a chemical reaction to produce the H2 plus bromine. Now you can see from this chemical reaction, actually the active species H will become stable H2 molecules and plus a Br. In this case, usually we know the Br is a very stable species, okay? Which means that from these chemical reactions, you kill the active species and you just produce is a very non-active species Br, which means that you cut down the chain branching reaction. For example, you kill the H out, then you may not have a chance to go through the reaction B. Okay, one of the chain carrier reactions be suppressed. Okay, and those Br continue meet with Br, then will become a more stable Br radicals. And here, additionally, H will be react with Br2, the bromides, and they always produce the very stable bromide. From these three chain reactions, you realize you may have a lot of hydrogen species, or we call this as an active chain carrier, and those chain carrier be killed and by the this serious chemical reaction, and you just produce the more non-reactive species bromide, and the chain reactions will be cut down. You cannot continue to produce a lot of chain carrier. Then the very fast chemical reaction will be slowed down, will be stopped. Okay. Now, in this sense, you will find out the influence coming from the CF3Br. They try to suppress the production of active species H and stop certain chain carrier reactions. Then those kinds of unstable combustion mechanism be suppressed or eliminated. Then they will return to a very nice stable cone frame and a very nice shape frame. Now, this kinds of experiment give us some idea. When you're dealing with the analysis based on the Lewis number effect, usually we evaluate the Lewis number based on the so-called original reactants concentration, right? That means that we do not care about the individual active species in a chemical reaction zone. Sometimes it is very hard for us to study the influence coming from the chemical reaction. Or we always study the influence of the chemical reaction from the bulk of the reactants, right? We say methane and we say oxygens, but in reality, in the reaction zone, actually there is no. If you look at the lean methane frame, you may not find methane inside of the reaction zone, right? Because methane already decomposed to maybe the CH or CH2 or CH3 or even OH and H. Those kinds of intermediate species exist boundary in the reaction zone, but you do not have a methane, right? And you may not have oxygen inside of the reaction zone because most of them, all the reactants, they start to decompose and they produce so many intermediate species into the chemical reaction zone. Which means when you're dealing with the discussion on Lewis number effect, we need to look at the species, the intermediate species inside the reaction frame instead of the species from the original mixtures. Okay. Now we cannot do it because you cannot measure very correct, very nicely, very correctly, very correct on the concentration of those kinds of intermediate species, because they are intermediate species very active, and we do not have those kinds of techniques to do the nice measurement to identify the concentration. Then you do not have a chance to study the Lewis number based on intermediate species. But this experiment tell you, when you look at those kinds of Lewis number effect that we call the diffusion process, right? Diffusion process basically is controlled by the molecular collision, right? But now we talk about the Lewis number effect in general. We're dealing with that, and we look at it based on the concentration variation of the reactants from the beginning. But now this experiment tell you maybe there is some inference we do not observe, and those inference will be very important to see they will get involved with real Lewis number effect, because for the diffusion process, for thermal or mass, actually they will be carried by those kinds of intermediate species. Okay. Now, this experiment just give you the idea. When you get involved with the HBr, and this HBr will kill the active hydrogen species and cut down some chain chemical reactions, and we try to remove those unstable mechanisms out. Then frame become stable and go back to the original stable, the very smooth Bunsen frame. And this just gives us the hint that in reality, you need to go to the deep to think about the diffusion transport of intermediate species, not just from the discussion from the original your fuel and the air concentrations. And however, it is hard right now to know the detail to measure the detailed concentration variation of the interactive species. Maybe in the future, if you can do the measurement of those kinds of our observation or our discussion will be more complete. Okay, this is just a very nice experiment, and to mention there is some advance needed for the combustion study. Okay, now we need to give you the some. We need to go back to the. Let me. We need to go back to our slide to tell you now we are in which slides. Okay, we already finished up to the 1.28 page, and then actually there is the additional small subject I do not want to talk very detailed. There is some kinds of influence coming from the acoustic. That means that if you have a sound, okay, those kinds of acoustic wave will give you some influence because there is a wave, right? And you realize premixed wave is a wave, is a propagation, right? It's a differential wave, and those waves will meet together. Then you will when you have acoustic influence come in, they will produce some kinds of instability. But I do not want to talk about that too much. But you remember, starting from the 1.29 page, and we will go back to the previous discussion on the cold flow structure described by the two-phase stagnation flow, as you remember, okay? And we use the experimental data to be compared with the theoretical and numerical predictions. And these figures tell you the radial velocity distributions for a different radial distance. And this is the actual velocity distribution. I think you understand it. And this one represents the actual and the radial velocity distributions in the stagnation point flow. And those cold flow structures can be used to estimate where is your premixed strength. You should remember and try to have a practice to learn how to justify or how to estimate the position of a premixed friend can be stabilized in the stagnation point flow or opposite jet flow by using the radial and axial velocity distribution in this cold flow. Actually, I always try to give you the basic understanding. When you try to analyze a burning flame, a reactive mixtures, you need to study the cold flow. Cold flow means no combustion, just flow, and try to analyze the flow structure. Then you try to bring your basic knowledge on the determination on the premixed frame position. I hope you understand how to determine the position of premixed frame, right? Based on the location. At these locations, the supply of your premixtures just balance with the consumption of your premixed frame. Then this frame will sit at this position. Okay. In this sense, we are telling you at these positions, the frame speed is just balanced with the supply velocity. Okay, and by this concept, you can use the cold flow to identify where is the frame sit. And the next one, when you ignite it, then there is some comparison for the flow characteristic for burning and non-burning structures, as I explained previously. And this is a temperature distribution for the methane flame with water and without water. Okay, and there is the actual velocity variation and radial velocity radiation uh, variations for the methane premixed flame with water or magnesium oxides, and we already explained very detailed. I hope you can go through again to go back to think about how the influence coming from the flame on the flow structures in the stagnation point flow. And next time we will give you the some introductions to the turbulent premixed flames, and we'll end the premixed flame burning sections. Then we will go to the diffusion burning sections. Now we stop it here and give you the some understanding. I try to mention here those kinds of experiment results as I explained earlier. You need to use it. I will give you the assignment. You need to have some practice to help yourself to identify where is the premixed flame positions in the stagnation point flow, or maybe in the Bunsen flame.